Andrey, Shanin. Who will speak?
So I will speak first. Raphael Assier. That's me.
Okay. 1 hour for your talk. Please go ahead.
Okay. Right. Thank you. So can everyone hear me correctly? Yeah. Right. Good. Okay. So in this series of lectures, we will try to give our view, in some sense, of complex analysis in several variables, and here by applied, well, we mean we will do stuff probably not in as much rigor as other people would like, and also in terms of application, what we have in mind are mainly waves. Okay, so which means that if you're in the audience and you have applications in mind that are not waves, but that you think could be this material can be helpful for that, then please let us know. So, okay, so I'm Raphael, but Andrey is just there. So, okay. So, yeah, so I will do the first two lectures, and Andrey will do the remaining two. Just before we start, why this this session? I will give some scientific motivation, but there's also a sort of more pragmatic motivation. Is that this topic of multivariable complex analysis is indeed covered in a list of textbooks, some of which that we have consulted and found useful are given here. This will be my only slide, by the way. The problem with this textbook is that I don't think they can be considered as easily accessible. Okay, they're mainly written, well, by and most of the time for pure mathematicians, and often some of the problem that they're interested to solve can be quite different from those that we would like to, for example, Wiener-Hopf, etc. And hence, I mean, some of the tools developed here can be used, but they're not easily accessible, and some different techniques should be developed to address problems that we're interested in our community. The first of these books, Shabbat 2 here, is, I would say, the most accessible of these, and can be considered as our book of reference for the main definitions, etc. of these lectures. There's lots of others. The one by Loré here, you can see, is the oldest, and in some sense he was one of the father of this area. So if you want to start with one textbook, it's probably best to start with the top one. That was the message. And now I will start. Okay. Right. So the first lecture will be focusing on. This is our first lecture on analyticity. In several variables. Okay. In particular, this means we will consider function W that are going from Cn to C. Okay, so we will then write something like W of Z1, Zn, where Zj is a variable in C, and we can write Zj is xj plus iyj, where x and y are the real and imaginary part of it. Okay. So before I get into more detail, I think the first thing to address is why. So motivation. And the first, I will talk about three different reasons why we're interested in that. And the first motivation is very much linked to to the topic of this program, and okay, Fourier. Okay. So if we, as we've seen before, if you imagine, I don't know, to do that I keep in mind having a problem, diffraction problem, say two-dimensional diffraction problem, have in mind half plane, for example, then it turns out that, and as we've seen in the previous lecture, is quite interesting to consider Fourier transform of a function f of x. So you have a function f of x, there is a real functions, and we want to take its Fourier transform that I will call for the purpose here w of z, which is integral between minus infinity and infinity of f of x e to the I z x dx. So the good thing is that we chose the same definition as for the Fourier transform, so that's good. Right? And so basically the heart in some sense of the Wiener-Hopf technique, as we were explained earlier, is that we have this x-axis, and so this is 0, and we integrate over the whole x-axis, okay? But as we've seen, if we split this integral into two parts, so here on x positive, and we say we integrate between 0 and infinity, okay? And on the green part, we will integrate between minus infinity and 0, so we can, well, define functions, okay? We can just give it a name, say w plus of z, this is this, and w minus of z. This is this. And these two integrals are referred to as half-range Fourier transforms. Okay? And the beauty of that is that when we have this z here, we can show that this stuff is analytic in the upper half plane, while this function here is analytic in the lower half plane. Okay? So this is, in some sense, what I would consider 2D physical problem. Okay? Whatever it is, but have in mind the half plane problems there. Okay. If instead of 2D we're interested in three-dimensional diffraction problem, so if I have 3D physical problem, then we tend to have to consider a certain function f, say, I don't know, what did I use here, x1 and x, so let's say x1 and x2, which will be a real function of two real variable x1 and x2. And well, it's useful to consider Fourier transforms, but since we have these two variables, we can take two Fourier transforms. So we have a double Fourier transform, but that will be naturally defined as, say, w of z1, z2 is of x1 z1 plus x2 z2 d x1 d x2. Okay, and now, so you see that this integration is performed on the whole x1 x2 plane now. Okay? So we can, if I write it like this, I integrate over all of that. Okay, and I can choose to say, well, with analogy to what I've just done here, I can also say, well, let's see what happens if we integrate just over this, and we then, if I integrate only over this region, I will get an integral between 0 and infinity, and an integral between 0 and infinity. And it turns out that this function, well, we may as well call it W plus plus of Z1 and Z2, can be shown reasonably straightforwardly, in fact, in the same way that you show that these ones are analytic in the upper half plane. You can use one-dimensional complex analysis to do this, but this thing is analytic in a set that is the equivalent of upper half plane here, but I will write upper half plane 1 times upper half plane 2. So what does it mean? It means this is the set such that im of Z1, say, positive, and im of Z2 positive, right? Okay. And this is useful. The problem comes if you want again to split your domain into 2 parts. Then you're left with the other part. Okay, and the other part is the remainder. And the question is, how did I call this? Yes, so we have, so similarly I can call this one quarter range Fourier transform, and the rest here I will refer to as 3/4 range. Nothing, okay? The question is, where is this analytic? Okay? And the answer to that question is in fact not trivial at all.
Is there not a temptation to split it into 4?
Yes, there is absolutely a temptation. So in fact you can split it into 4. Each of them will be analytic into a subdomain like this. But this is in fact limited in terms of what you can then do with that. Okay? But I will probably talk about the 4-way splitting, but at the workshop rather than here. But you can develop some tools of trying to find out where this thing is in fact analytic. So this was one motivation, because how then do you go on to showing that this kind of stuff has some analyticity property, etc. Okay. So, and obviously here, if you had to have the half-plane problem in mind, so Sommerfeld problem, this is what you will encounter with quarter-plane problems, so the equivalent. Okay, another application is for waveguides, and in particular transient phenomena in waveguides. Why? Okay, so if you take wave propagating in waveguide or waveguides that somehow are linked to each other, you often will recover what we all have encountered as dispersion relation. What does dispersion relation mean? It means if you have, let's consider that we have one-dimensional waveguide, but we have time problem, then it means that the solution of your wave field in here could be rewritten as something like this. Infinity of a certain function divided by another one, and then you have d omega. Alright, where d, when you have d of omega k equals 0, this is what we call the dispersion relation. Okay. And in fact, dispersion diagrams or wave phenomena are a very well studied thing. And what does it mean? Dispersion diagram, it means look at singularities of, well, d or 1 over d of a over d in R squared. So we're looking, for example, for zeros of these. such that k and omega are real, okay? And so this tends to give propagating wave. Okay. But in waveguide, there's not just propagating wave, there are transient phenomena that can occur, okay? So, for example, if you look now at the singularity of the same thing, but in c squared, then you will get transient phenomena. So, for example, forerunners or leaky waves or this kind of things. And on that front, I mean, Andrey has written some papers on that. And the last, so this was my motivation, my second motivation, and the third motivation, which I will not say too much about, is discrete diffraction problem on 3D lattice. Okay, so, well, Dave just did a little bit of something discrete problems rather than. Okay, and this will be discussed in lecture 3 or 4, depending on our time management. Okay, so this was just to give you an idea of why starting looking at functions that have more than one complex variable can be interesting, and hopefully to convince you that it will also be very helpful to whatever problems you're looking at, especially in 3 dimensions. Okay, so now I will be a bit more academic in some way, and some more not for very long, but we'll just do some lecture type thing. So we will start with the beginning. And I will give a few definitions and a few theorems, but not too many. This should. Definition, okay. We say that a function w that goes from Cn to C satisfies the Cauchy-Riemann conditions. I will say CRC. If dw over dxj plus I dw over dyj equals 0 for j equal n. Okay. So if you think well, obviously to the complex analysis of one variable, then if you put n equal 1 and you do this, you take the imaginary part and real part of w, that gives you 2 equations. These are your 2 usual Cauchy-Riemann equations. Only. Okay. We say that the function w is holomorphic and holomorphic is also something that is sometimes called C-differentiable at a point, I don't know, A belonging to Cn if, well, W is R-differentiable as function that goes from R2n into C, Okay, so obviously Cn and R2n are connected. Is because of the top thing here, and W at A, sorry, at the point A, and W obeys the Cauchy-Riemann condition in a neighborhood of A. Okay. Right.
Is that equivalent to the derivative of the Cauchy-Riemann conditions?
Yeah.
Equivalent to derivative of W with respect to ZG?
ZG bar.
Z equal to 0?
No, this is DZG bar. But we will go through that in more details. But yeah, this thing is this sometimes also known as that. Okay, so
Maybe this condition can be exchanged, differentiable in a neighborhood and Cauchy-Riemann in a point.
Well, probably, but yeah. But I think this is correct.
Can exchange.
Okay.
Because if you expect Cauchy-Riemann in a neighborhood, then it should be differentiable.
Yeah, true. That's correct. Yes. What can we say? So first thing that can be said. So that's the first of the only two theorems that I will write. Okay, so this is quite a long time ago. So if omega is a domain in Cn and W is holomorphic, okay, let omega Cn. Sorry. Yeah, so that's the thing. If W is holomorphic on omega with respect to each variable separately. So what does it mean? You fix, say, if you have two variables, say z1, z2, you fix z2 and you look at this function as just a function of z1, and hence for this, well, what it means to be analytic, etc., is well defined. Okay. Then W is homomorphic on omega. Okay, so this is in fact a very, very strong result. It means that to be holomorphic as a function of Cn, you can fix all the variables but one, look if your function is holomorphic, and then repeat the thing, and if it's the case, then you can have some results in some sense. You have C differentiability with respect to each variable is the same as C differentiability with respect to all at once. Okay. And this is, so first, quite deep in some sense that, for example, this is not true for R differentiability. Okay, so if each of your, if you have a function f of x and y, if it's differentiable with respect to x, differentiable with respect to y, it doesn't mean it will be differentiable as an R squared function. We can discuss later. I can give you examples, and this theorem is in fact not particularly trivial, in the sense that even in most textbooks there's no evidence, enough space to prove this. Okay, this is in Shabbat 2. It is not proven, it's stated, and a few lemmas as well. So to get there was an enormous amount of work there, using very complicated tools of topology, etc. But we will admit.
Can you give us an idea why it's so hard to prove?
Well, it is because the topology of neighborhoods in higher dimension, and I will get onto that now, can be very difficult to play with. Okay, and to, well, visualize to a certain amount. But yeah.
I think if you show the real R2 example,
Yeah.
then it probably will be clear.
Okay. So R2 example. So if you have, say, you take a function is xy divided by x squared plus y squared. Okay. So you fix y. So and it is for xy different from 0, 0, and it is 0 for xy equals 0. So you can take partial derivatives of these, df, dx, etc. They are well defined, etc. But this function is not differentiable at 0, 0. In fact, it's not even continuous as a function of r squared. Okay? Why? If, say, you look at f of x and x, because obviously there's different ways to go to 0 in r squared. So if I decide to go to 0 like y equal x type of thing, then this will give you x squared over 2x squared, and this tends to 1/2 as x tends to 0. Yeah? But if I decide to go it, I don't know, f of x and 2x, this will be want to have 2x squared divided by 5x squared. This tends to 2 over 5 as x tends to 0. Okay, so that function f is differentiable with each of its variables, but not even continuous as a function of r squared. Okay, so, but this is not the case in C.
Do I remember correctly that in Hartog's proof, the most difficult part is proving continuity?
Yeah, well, if you've read the whole thing, then good. But yeah, yeah. I have to say, I don't know all the steps of Hartog's proof. This is part of the thing I was saying, that things are very, very difficult, not accessible in some sense. Right. Okay, and since we are in a Wiener-Hopf setting, I'll just give one last theorem briefly again. I'm not going to prove anything, but this is Liouville's theorem. We'll see if you have, if W is holomorphic on Cn and bounded, then it is constant. Okay, so Liouville theorem works in higher dimension. That's one of the messages. So in some sense, there is some hope in the Wiener-Hopf case. Right. We were discussing neighborhoods earlier, so I just want to.
One question.
Yeah.
Is it somehow unsurprising that it works because your restriction is even more, right? So
Yeah.
considering the smaller class.
Or you can also use the
So this
Hartog's
is not hard.
one.
So this is not a very hard.
No. This isn't hard. But I thought I should mention it since we all want to use these things. Now I was talking a bit about neighborhoods earlier, and I just want to give an example of what a neighborhood can be. There's loads of different sets like this that are defined, but I will talk about the most natural in my opinion. So if you have, say, in C squared, say you have then two complex planes, Z1 plane and Z2 plane, and then you can pick a point in C squared. We'll have something like this. You can represent it like this. We'll have a coordinate in Z1 plane, and you can, if you wish, draw some sort of, this was supposed to be a circle, some sort of circle around here, and some circle over here. Okay. So if you have a point, say C equal C1, C2 in C squared, then we have this C1, C2, and you can define, so this is the center, and you can define the radius. R1, R2, and this one is probably something like this. I want R1 and R2 to be positive, so these are my R2 and R1. Okay, so this is a typical neighborhood, so you can write it like this. U, the center, and the radius is just a set of all z in C squared, so that mod Z1 minus C1 is less than R1, and mod Z2 minus C2 is less than R2. Okay. Right, so now imagine that I call, say, the interior of that disk, I call it D1, and the boundary, the circle, is gamma 1. And here I can have something like this. This is D2, and the circle is gamma 2. Then what's an interesting question is, what is the boundary of that neighborhood? Okay, so in C you have a disk, you take the boundary, that's the circle layer and stuff. Done. Okay, so but in C squared, for example, here we will write, yeah, so I will go to the next. So the boundary of U, okay, so I hope, so you notice that I've got strict inequality sign here. So in fact, if you think of the boundary of U, you can always write it something like that. As long as one of these inequality is violated, so you get something. So you can have something like this, D1 times gamma 2. So if a point is inside the disk on the Z1 plane, but on the boundary in the Z2 plane, so that's one thing. But you also have this one, okay? The other way around, I take a point in the disk in the Z2 plane and a point on the circle in the Z1, but we also have this. Okay. Well, why is it interesting? For this reason, if I look at U, that we are there, then this space here, I will write like this. Yes, is a space of dimension 4. Okay, because you can imagine like that. Now, the boundary. This thing is, we can move on the circle, that's 1. We can move inside the disk, that's 2. This is 3. This is 3. And this is 2. We've got 2 lines, okay? So we have a space that when you take its boundary, the boundary is a union of spaces of decreasing dimensions. And this obviously does not really occur, well, we only have that once in C, that's just a circle dimension 1 of a disk dimension 2. But you have lots of different dimensions, and then if you go higher in dimensions, then you will get such sequence as well. Okay.
So you get all the smaller dimensions.
Well, but not 1 in that case.
Oh, it's kind of trivial.
Right? And this thing here has a name for the polydisk. This stuff here, the product of the disk, is called the skeleton of U.
I was going to say that you don't want to lump them all together. There are times when you want to treat the one, as you say, the sort of the skeleton as separate objects.
Yes, well, you do want to treat it as a separate object, as we will see maybe in lecture 3 or 4 again. If you think of Cauchy integral formula, then this is this kind of things that come into play. Okay, so this is a product of circles. So people who have done topology among yourself realize that this can be alike to a torus. Okay. Right. Now, a few questions. Well, one question: how do we get holomorphic functions. Okay, this is we've described this stuff, but what are these objects? Okay, so well, we can think of three ways. A bit like what we do in C, really, is by formula. Okay, there is sets of functions that we know are well-defined functions, polynomials, etc., and so combinations of these, you'd expect that they are. So something like this. So a function like, say, z1, z2 is, what did I choose? z1 plus sine of z2 plus, I don't know, square root z1. Okay, so a function like this, it's quite clear, looking at this, that this will be holomorphic everywhere, but at certain sets of problematic points. Okay, so away from the places, for example, when z1 is 0, this should be fine. Okay. B. By Fourier transform. So, for example, we've seen up there that if I take a Fourier transform like this, I know its analyticity domain, and I know that my function w plus plus is holomorphic in, say, upper half plane 1 times upper half plane 2. And another one is, I will actually put it there. And the last one, say, by implicit / inverse functions. So if you take now, if we consider a function, let d of a certain variable w, z1 and z2 be holomorphic in C3, okay, then the solution w of z1, 2, so whatever this means, of the equation w z1 z2 equals 0, then we can show there's a theorem that tells you that this thing that we can define at least locally is holomorphic where okay, so for example, so you can then embed thing in a higher dimension and then use this like that. Okay. So typically, imagine you have, well, so this is in C3, but imagine you have W, you're interested in what's going on for a function like this, for example, then you know that for this to be true, this must be solution of w squared minus z1 minus z2 equals 0. This function here is clearly holomorphic in C3 because it's just a polynomial, and then you can apply this stuff. Okay. Right. And this type of approach can be very useful when we will try to attempt to describe singularity sets of various functions. Okay. And I think I will skip the just something and get into some more okay. Section 2, which obviously is of crucial importance to zeros, poles, and branches. Okay, so as we've heard in the previous 2 hours, these objects, whatever they are very fundamental and need to be understood if we want to play with function of complex variables. Okay. And the main point that I want to make here is obviously in C we are used for these objects or these zero poles and branch points to be isolated points, a set of discrete points in C, right? Okay, well this is not going to be the case anymore in higher dimensions. So I will illustrate this in C squared and start with zero sets. Okay, so if you let well, W be holomorphic in C squared and consider the set big Z W is all the points in C squared such that W of Z1 Z2 is equal to 0. Okay. So it turns out that obviously we have 4 degrees of freedom in the sense that we can move x1, y1, x2, y2, and here we have 2 restrictions. The real part of W has to be 0, the imaginary part has to be 0. So this thing here, ZW is an object of dim R equal to, this is an object of dimension 2. Okay, so yes?
You have already example here.
Sorry?
You have an example here.
Yeah.
You can explain on this example this definition.
Yeah, well, I will do one. If you let me. So this is all the points. So in that case, there was for 3 dimension. I'll do it in 2. So and it turns out that again that will be very much clearer in another example that we can write this set as a new union of a finite set of such object Li, which are smooth 2D object by object in 4 dimension that lives in C squared. Okay, by object I mean actually manifolds, and manifold we will discuss this in the next lecture. And this L, they are called zero two lines. Okay, this is how we'll call them. And well, interestingly, these lines can intersect. Okay, these 2 lines can intersect, and it's possible to show that if you take say I different from k and you look at a certain line Li inter Lk, then the dimension of that thing is 0. So in a sense the intersection between these 2 nice smooth 2-dimensional object in 4 dimension is a set of discrete points. Okay. Example that will make things easier. If you consider W of Z1 and Z2 to be equal to, well, Z1 squared minus Z2 squared. Yeah? So this obviously can be rewritten, factorized in the usual way. Okay. So here, my 0 set of W, ZW, this is just going to be L1 union L2, where L1 is the set such that Z1 equals Z2, and L2 is the set such that Z1 equals minus Z2. Okay. So we described here entirely, well, the 0 set of this function. And to go back to what I was saying here, then if you look at L1 L2, in that case, this is 0. Okay, so we have a function of 2 dimension has a 0 set of 2 complex dimension, has a 0 set that is a union of 2 objects that each have dimension 2, and the intersection is just a point. Right, so now that we've defined 0 sets, it's actually reasonably simple to talk about.
Excuse me.
Yeah.
They cannot have intersection one-dimensional, right?
Well, in general, no, because if you look at manifolds, if you take, say, the intersection of 2 manifolds of dimension, well, if you have a manifold of dimension m1 and a manifold dimension m2 that live in a space of dimension big M, say, then the intersection between these two in general will have a dimension that is m1 plus m2 minus big M. Okay. But I don't want to go into too much detail. You can take my word for it on that.
Why do the li have to be smooth? Why can't you get some kinks in them or something?
Well, these li are some mainly because I was assuming that my function was holomorphic. I think that's the reason. And also, why can we always write it like this? It has some sense. These li are called some irreducible parts, irreducible factor of this 0 set. But again, yeah.
Your function is z1 minus z squared. So what
Sorry?
z1 minus z2 squared. So
Yeah, I will do this function. I will do it. Okay. Okay. Right, what else do we have? Polar sets. Okay, so the equivalent of poles. So if you let G1 and G2 be holomorphic in C squared, and we can consider W of Z1, Z2 is equal to G1 of Z1, Z2 divided by G2 of Z1, Z2, then in that case we will say that the polar set of W is in fact the same thing as the 0 set of G2. Okay. Then polar set that I'll write PW is equal to 0 set Z of G2. Okay, and the same, the two lines Li of this 0 set G2 are called polar 2 lines of W. So again, that's the extension of a pole to a higher dimension, and
What about the intersections of the 0 sets, the numerator and denominator?
Sorry?
Well,
Yes, oh, exactly, okay. If Li intersect Lk, then the intersection is called secondary pole of W. Okay, so yeah, they will intersect.
The question was, if they have just the cancellation between G1 and G2?
Well, then this is a removable pool. Well, we do exactly the same in 1D complex analysis. That's not a problem. Here, okay, so here I could have, I'm not going any further. I could also define the order of a pool, etc. But I will not do that now. Because I just want to talk in the last 10 minutes or so about something that is of primary interest to everyone in at least the wave community, Wiener-Hopf community, etc. And these are obviously branch points in C. Okay. Nonsense. Okay. And I have to somehow apologize in advance here, but it turns out that, you see, the list of all the books that I've shown you, almost nowhere is the notion of branching a function of several variables actually treated, or even sometimes just not even mentioned. And so I will try to give some sort of idea of what we mean by that. First of all, I need to be able to parameterize a two-line. Okay, so we take a two-line. Remember, it's a smooth 2D manifold in 4D that we've encountered there. So imagine I've got a two-line L. So typically, obviously I can't draw in 4 dimensions, but if you have an L, and if you take a point S that belongs to your two-line, okay, then locally, the way of doing this is to do a local change of variable to some variable alpha and beta, such that in some sense alpha is like this and beta is like that. What does it mean? It means that S, first of all, is alpha equals 0 and beta equals 0. And also we want to choose these variables such that locally L is described by alpha equals 0. So alpha and beta are themselves complex variables. Okay, so this is the description of a two-dimension set, right? Okay. So, and this is the easiest way to sort of deal with this thing, to have some sort of transverse variable alpha, but that is complex. Okay. Right. And now, with the help of this, we can try to discuss the notion of branching in higher. Or at least here, I drew everything in C squared, but we can think of. Okay. So the idea is as follows: take a two-line L. Take a point S that belongs to L. So L is a two-line. S belongs to L. Now we will take a point P that does not belong to, okay? P that doesn't belong to L, and we will choose another point that I will call S dash. S dash that doesn't belong to L, but is some sense close to it. Okay, so that means that I could describe it in my local variable around the point S, such that, for example, say S dash, we could write S dash is alpha equal a certain epsilon positive e to the I big phi, and beta equals 0. Okay, so this stuff does not belong to L because L is defined by alpha equals 0. And now the nice thing is that what I want to do basically is to find a way of explaining what it means to, in 1D, to turn around a point. Okay? So here we need to describe some sort of path that winds around a two-dimensional object in 4 dimensions. Okay? But in fact, so P and S prime, you can always link them together. And here, with this definition, I can define, say, a path sigma that is in the local coordinates alpha beta. I can say is epsilon e to the I big phi plus t, and beta equals 0. So for t belongs to 0 and 2 pi. Okay, so what does it mean? It will generate some points, that in some sense will go back to here, but will never cross L, because I will never have alpha equals 0. Yeah? So this gives me some sort of path that we call sigma. And I go to that point here. And then I can go back to there. Okay? So basically, then we will see branches. Now we can sort of describe what we mean by branches. So we say that S belong to a branch 2-line of a certain function W if in our little diagram W of P is different from W of P dash, where P dash is me coming back to the initial point having rotated around that thing. Okay? So, and another way of viewing this, if you prefer to think of branch point, in fact it's quite useful, is that if you cross-section this with the alpha plane, in the alpha plane, so this is now just a plane, a complex plane, as we all know it, then alpha equals 0 is a branch point. Okay? And so then from that sort of definition we can think of defining order of branches, how many times you turn around exactly. Yeah?
Is it clear that the only singularities are poles and branches?
Well, it's not the case in C, so probably not in C squared, right? So you also, I imagine, have essential singularities and these kind of things, yeah. But again, I think just these kind of things, there's almost nothing that exists in the literature about that.
Isn't that because you can go to higher dimensions, so you introduce another sort of complex variable to get rid of your branch?
Yeah, but this is a bit what's going on here. So I've got 5 more minutes, I will, yes. And I want to, in the last 5 minutes, I will show you an interesting example that maybe it will relate to some of you, maybe at least John, maybe. Okay, I will consider a function and this is, I will finish with that. So W of Z1, Z2, well, in some sense that's linked to Gennadi's question as well, is something like root of Z1 minus root Z2. Okay. This type of functions can be, in fact, quite complicated to study. And this type of things occur naturally. I mean, when you look at factorization of the type of kernel that you get when you do double Fourier transform of wave problem, if you attempt to do some factorization of this, you will incur functions that are a little bit similar to these. And in particular, for example, if you think of a function z1, z2 to be square root of z1 squared minus z2, then it makes sense to, factorize this as something like this, which is our w, and the other one Okay, so we're focusing, this is our W. So this is where such object can come from. Okay, so now, okay, we have the intuition, well, of what this sort of thing means, and it means that if we look at the branch set of W, I don't know, let's call it like this, BW, it will be L1 union L2, where L1 and L2 are two branch, two lines, and L1 is just given, not, I mean, when you look at it, L1 is Z2 equals 0, and L2 is Z1 squared equal Z2. Okay, obviously, if I'd asked you earlier at the very beginning of this lecture, what's the branch possibilities of this function, you would have told me this, right? So, okay, in some sense, this is related. What is interesting here? Well, first of all, if you look at the branch set of F, it's only that one. This is a branch set that occurs just because of the factorization that we've made. Okay, again, this is something that happens in 1D complex analysis. But what is very interesting about these two sets is that if we look at them in a special plane that is this one, real part of Z1 here and real part of Z2 here. Okay. Then, well, Z2 equals 0, the projection of this branch line onto that plane is just going to be this. Yeah, so this is in some sense the projection of L1 on this plane. Now, if I look at the projection of L2, I will have something like this. Well, this looks like a parabola, right? So I get something like this, and here I get something like this. Okay, I will explain to you why I chose different color, but this is the projection of L2, and this is the projection of L1. Well, they do intersect somehow. If I do L1, L2, this is again just the 0 point. But this is not an intersection in the sense of a transverse intersection. So these two objects here are somehow tangential. Okay, so they do not cross, but they're like touching points. And this is very interesting because this can lead to some particular situation.
I'm sorry.
Yeah.
Can you change the notation? You have two L1s there. You have green L1.
Oh, sorry, this is L2. This is this, sorry. This is just, I've just decomposed L2 into two colors. Sorry, this is L1, this is L2. And this touching point can lead to some interesting phenomena. For example, in fact, if you look in that plane here, you will realize that it is possible here for Z1 to be equal to root Z2. So these points, if you look at this function now, if you think of it as a real-ish function, they have problems. I mean, what's underneath the square root can become 0. So this is branch 2 line in some sense, in the sense that we've defined it here. But if I look here, these points here are actually regular. In a sense that if I've got Z2 positive and Z1 negative, then what's inside the square root cannot be 0. Okay? So it means that somehow in the high-dimensional world, the red part and the yellow part of my branch 2 line are two samples of the same object and that behave very differently. Okay? And this, we believe, is due because of this type of tangential situation.
So can I ask a dumb question?
Yep.
We're just looking at a subspace of Z1 and Z2.
Yeah, we're looking at a projection on this. Yeah.
You say it's a projection, it's a slice through, it's not a projection.
Well, it depends how you define a projection. Yeah.
Well, but
we call
have
it.
looked at the imaginary part of Z1
Yeah.
and Z2, or any other your picture would look different. So what's
Yeah.
special about
Well,
this?
because here this is to highlight that particular point. I mean, this
But that
is
might
easy to
happen somewhere
visualize.
else in a more complicated.
Yes, of course it can happen somewhere else, but then you can always change your variables. I mean, that's the idea of picking your alpha and beta nicely such that this kind of stuff happen. Okay.
Will it quite often happen somewhere?
Sorry, yes.
But in geometry, people often talk about non-transversal intersections. And
Well-
we regard that as the normal case.
Yeah.
But here you're considering this abnormal case.
Well,
Yeah.
I'm not saying if something is normal or abnormal, I'm just saying this situation occurs, and in fact, when dealing with diffraction problems. And the situation of the transverse case, they also occur in diffraction problem, but for poles. And the polar set tend to be a more, yeah. So that, just wanted to say last word is that, yeah, this is in some sense our take on branching, because there doesn't seem to be existing much things, but some things can be done and some real results can be obtained about this for some diffraction problems. But obviously, why are these sets important, especially if you think of wave fields? When you do your inverse Fourier transform, what are wave fields? They are singularity in the complex plane. They are picked up when you deform what's contour. Okay, so there's two important things here. The singularities are important. Singularities are not isolated, and in fact it can be shown that this line here always go unbounded, and you can find as big as you want value of z on each of these lines. And then I've said something about contour deformation. Well, what does it mean? What does it mean to deform contours around such things like this? And I think this will what we will try to talk about in the future lectures. But before that, we will need a bit of tools. So tomorrow I will do a lecture, and that is somehow unrelated to complex analysis to start with. So that will be based on ideas of differential forms and manifolds. But so if you've done that course recently at university, no need to come. But if you're interested to know a bit more about differential forms, which then will be used in a complex settings in lecture 3 and 4, I hope you can make it tomorrow.
But is it right to define L2 in that way? Because if you're talking about the branch set of W, root Z2 lives in a half plane, doesn't it? So by squaring it, you've generated the yellow bit, and that means saying the yellow bit goes away, but the yellow bit shouldn't have been there.
Well, but you see what I mean? It was somehow there in that one. So that's the weird thing. Yeah. So that's one of these, and somehow because L2 exists for that one, you see. So L2 is an object, and it turns out that for a certain function, this object has two samples of it.
But if I was just talking about the branch set of W, would it not be right to just put a constraint on that definition for L2 and say that that Z2 is
in fact, this is I've plotted this thing, and then this is what I've sort of tempted to do on that diagram.
So what? If I'm just thinking about a particular function, it's going to be the case that these lines just can suddenly end. When they touch another one, they can just stop. And that's
yeah, well, in that projection, yes, but in fact, not. That's the That's so.
Just thinking of applications, is it often the case that your W is the frequency omega?
Not here. No, W. I more think of here. I think about the double Fourier transforms.
But in general terms, when you have the dispersion relation in the
so
omega and k.
No, but yeah.
The real frequency.
Yeah. So when I had this,
Z to the kx.
this was omega, but not W. So.
Yeah.
So omega here is indeed the frequency when it's real, and this can be considered more as, when I have the dispersion relation, I would consider these as variables, not as functions. So this, I will make omega and k complex and try to.
So in this framework, if you fix the value of W, and then look at what the topology is in the Z1, Z2 multiple plane, that's a significant object. That's a slightly different question.
Yes.
From what you're drawing here.
Yeah.
Very relevant question.
Yeah, it is, and not trivial at all.
Yeah.
So at least, the aim was just to say, okay, can we talk about pole branches and and zeros? The answer is yes, but they are complicated objects. Yeah.
I'll ask a dumb question.
The worst ones.
Did you want to specify?
No. I'd like to invite people to ask extra questions.
So, is there anything useful in quaternions?
Well, quaternion you don't need to this because we define here, you see we define a function that goes from Cn to C. I would imagine quaternion being useful if you want to go to Cn to Cn. So if you want, because here, for example, we never have to multiply one point by another. So there's no such thing as I never have to use Z times, I don't know, another Z star, whatever that means. I don't have to define a multiplication to do analysis of such functions. Okay, you can, again, I didn't mention this, but you can talk about series expansion, okay, in the same way. Again, you've got analyticity with series expansion, holomorphy, the two tend out to be the same, etc. But yeah, already in C, it's a difficult task to go and you have to prove that the two are the same, blah, blah, blah. Here it's complicated. But yeah, series expansion is useful here. For quaternion, well, I believe this is sort of two different kind of things because you'd want to multiply points together, which we don't do here.
Well, it's an extension of defining complex numbers from real numbers. And,
yeah. Well, yeah.
But we know the Cauchy-Riemann relations are so restricting for quaternions; they're useless for
yeah.
in terms of
Yes.
generalizing.
So that's it. So in the here we have such object. In some sense, you can think of a dot product. But in quaternion, you want that this stuff also belongs to Cn. So here we just define these things such that they belong to Cn, and this is fine. Yeah.
May I add a little bit? You are absolutely right that this is another kind of things, quaternion or Clifford numbers, but there is analysis on these objects.
Yeah.
But this analysis is different from analysis in Cn.
Mm-hmm.
That is the point.
Yeah. Yeah.
But as for impossibility, it is not exactly correct.
Of course.
Because there is a Clifford, as well as analysis on Clifford numbers, so-called Clifford analysis. We know a great specialist in this area, for instance, Anastasia Fazor. A lot of people work in this, and analysis exists, but it is quite different from analysis in C. This is
No, but I am not saying it doesn't exist. I'm just saying typical object that we want to study are Fourier transforms. Fourier transforms, well, they have values in C as far as, or maybe you can define.
What can be added to your lecture? Of course, we have to understand that the domain we speak here about are quite different from the domain in a complex plane.
Mm-hmm.
For instance, the domain in C2 do not separate C2 in two parts.
Mm-hmm.
What is the most impressive thing?
Mm-hmm.
And this plays a crucial role when we go to analytic continuation.
Yeah.
This is crucial for this.
Yeah.
Another point you mentioned, but not too much mentioned, that all sets you introduced, all these sets are in fact infinite.
Yes,
sets.
I did say
They
that.
go to infinity.
Yeah.
Can you imagine if you have a set of points that 1 square plus that 2 square equal to r square? This set goes to infinity.
Yes.
In fact.
In fact, we will talk a lot about this particular one.
Yes, it is not a bounded set, it is unbounded set, because one of the variable can be as big as possible, and another one compensate it to have a square. This is a crucial difference between C and C2.
Yeah.
This you explained in your lecture.
Okay.
Thank you.
Well, thanks.
More question?
I think we'll go break for lunch. The questions can be asked.
Can be edited.
Fine.
Yeah.